Dear students, linearity property in Fourier transform. If C1 and C2 are arbitrary constants, then Fourier transform of C1 f1x plus C2 f2x is given by C1 f of f1x plus C2 f of f2x. Similarly, Fourier sine transform and Fourier cosine transform also satisfy this linearity property. That is, fs of c1 f1x plus c2 f2x is c1 into fs of f1x plus c2 into fs of f2x. Similarly, fc of c1 f1x plus c2 f2x is equal to c1 into fc of f1x plus c2 into fc of f2x. Next property is change of scale property. If fp is the Fourier transform of fx, then 1 upon a f of p upon a is the Fourier transform of f of ax. Corollary 1, if fs of fx is equal to fsp, then fs of fax is equal to 1 upon a fs of p upon a. Similarly, for cosine transform, if fc of fx is equal to fc of p, then fc of f of ax is equal to 1 upon a fc of p upon a. Next property is shifting property. If fp is the Fourier transform of fx, then e to the power minus ap into fp is the Fourier transform of f of x minus a. That is, f of x minus a is equal to e to the power minus ap into fp. Next is modulation theorem. If fx has the Fourier transform fp, then fx into cos ax has the Fourier transform half of fp minus a plus f at p plus a. Then we have results for derivatives, Fourier transform of derivatives. If fp is the Fourier transform of fx, then ip into fp is the Fourier transform of f dash x. Here it should be capital Fx. If fp is the Fourier transform of, or you write here small f dash x. If fp is the Fourier transform of fx, then f of nth derivative dnf upon dx to the power n is equal to ip to the power n into f of p, provided the first n minus 1 derivatives of fx vanish identically as x tends to plus minus infinity. Then we have convolution theorem. If f of fx and f of gx are Fourier transform of the functions fx and gx respectively, then Fourier transform of the convolution of fx and gx is the product of their Fourier transforms. That is, Fourier transform of fx star gx is equal to f of fx into f of gx. Now let's take few examples. Find Fourier sine transform of e to the power minus ax upon x. So by definition, Fourier sine transform of e to the power minus ax upon x is integral 0 to infinity e to the power minus ax upon x into sine px dx. So suppose that this integral is I. So I is equal to 0 to infinity e to the power minus ax upon x into sine px dx. Now our aim is to calculate I. So we differentiate with respect to p under the sign of integration. So we have di upon dp is equal to 0 to infinity e to the power minus ax upon x del over del p of sine px dx. Now partial derivative of sine px with respect to p is x into cos px. So x will get cancelled. So we have 0 to infinity, this is infinity, 0 to infinity e to the power minus ax cos px dx, which is equal to a upon a square plus p square by this formula. 0 to infinity e to the power minus ax cos bx dx is a upon a square plus b square. So therefore, integrating with respect to p, we have I is equal to tan inverse p upon a plus a. Now when p is equal to 0, if you put p is equal to 0 here, tan inverse 0 is 0, so I is equal to a. Now from equation 1, if you put p is equal to 0, then sine 0 is 0, so therefore I is equal to 0. So therefore combining these two, we got a is equal to 0. That means I is equal to tan inverse of p upon a. Second example. Solve for fx the integral equation 0 to infinity fx into sin xt dx is equal to 1 when 0 less than or equal to t less than 1. This is equal to 2 when 1 is less than or equal to t less than 2, and this integral is 0 when t is greater than 2. Now by the definition of Fourier sine transform, this is 0 to infinity fx sin tx dx is nothing but fs of t. So therefore fst is equal to same thing, 1 when t 0 less than or equal to t less than 1, 2 when 1 less than or equal to t less than 2, and 0 when t is greater than 2. Now we want to find out capital Fx. So by the definition of inverse Fourier sine transform, we know that capital Fx is fs inverse of fst, that is 2 upon pi 0 to infinity fst sin tx dt. So now we break 0 to infinity into 3 parts: 0 to 1, 1 to 2, 2 to infinity. 0 to 1 fst is 1, 1 to 2 fst is 2, and beyond 2, 2 to infinity, this is 0. So integrating, we have integral of sin tx with respect to t is minus cos tx upon x, then 2 times minus cos tx upon x whole square plus 0. Now put the limits, we should get 2 upon pi x into 1 plus cos x minus 2 cos 2x. This is 2 times minus cos 2x cos tx upon x. Limits of t are from 1 to 2. This is not square, limits are t from which is equal to 1 to 2. So we get 2 upon pi x, 1 plus cos x minus 2 cos 2x. Okay, now we take two more examples. Find fx if its Fourier sine transform is p upon 1 plus p square. So by definition, f of x is fs inverse of p upon 1 plus p square, which is equal to 2 upon pi 0 to infinity p upon 1 plus p square sin px dp. Now multiply and divide by p, so we have this 2 upon pi 0 to infinity p square into p upon 1 plus p square sin px dp. Add 1, subtract 1, so we have 2 upon pi 0 to infinity p square plus 1 minus 1 upon p into p square plus 1 sin px dp. Now we can break into two parts. So this is 2 upon pi 0 to infinity. Here p square plus 1 will get cancelled. So we shall have sin px upon p dp minus 2 upon pi 0 to infinity sin px upon p into p square plus 1 dp. Now value of this integral is pi by 2. We have already done this in lecture 4, problem number 7. Put p is equal to 0 there. So this is 2 upon pi into pi by 2 minus 2 upon pi 0 to infinity sin px upon p into p square plus 1 dp. So therefore f of x is equal to 1 minus 2 upon pi 0 to infinity sin px upon p into 1 plus p square dp. Now our aim is to calculate fx. So we differentiate again with respect to x under the integral sign. So df upon dx is equal to derivative of 1 is 0. So minus 2 upon pi 0 to infinity 1 upon p into 1 plus p square del over del x of sin px dp. Now derivative of sin px with respect to x is p cos px. So p will get cancelled. So we have df upon dx is equal to minus 2 upon pi 0 to infinity cos px upon 1 plus p square dp. Differentiating once again, because we still have got integral sign here and we got here sine, so we differentiate once again. So d2 upon dx square is equal to minus 2 upon pi 0 to infinity 1 upon 1 plus p square del over del x cos px dp. Now differential of this is minus p sine px. So therefore d2f upon dx square is minus 2 upon pi 0 to infinity minus p sine px upon 1 plus p square dp. Minus minus will get cancelled, so we have 2 upon pi 0 to infinity p upon 1 plus p square sine px dp, which is equal to f of x from equation number 1. This is equation number 1, and we got the same expression. So therefore d2f upon dx square is equal to f of x. So d2f upon dx square minus fx is 0. Now to solve this, we find out auxiliary equation, which is m square minus 1 is equal to 0. So therefore m is equal to plus minus 1. Now because in this case right hand side is 0, so therefore we just find out complementary function, and that will give us the solution. So we got the solution fx is equal to a e to the power x plus b e to the power minus x. And differentiating, we get df upon dx is equal to a e to the power x minus b into e to the power minus x. Now we want to solve for a and b. Now when x is equal to 0, from equation number 2, this is equation number 2. So when we put x is equal to 0, this integral is 0. So therefore fx is equal to 1 when x is equal to 0. So when x is 0, fx is 1. So put x is equal to 0 here, e to the power 0 is 1. So therefore a plus b is equal to 1. Now we put x is equal to 0 in equation number 3. So we get df upon dx is equal to minus 2 upon pi 0 to infinity dp upon 1 plus p square, because cos of 0 is 1. So integrated, we get minus 2 upon pi tan inverse p 0 to infinity, which is equal to minus 2 upon pi into pi by 2, which is equal to minus 1. So therefore, since f dash 0 is equal to minus 1, df upon dx is equal to minus 1. So therefore if we put x is equal to 0 here, we get a minus b is equal to minus 1. So solve these two equations, a plus b is equal to 1, a minus b is equal to minus 1. We get a is equal to 0 and b is equal to 1. So therefore solution is given by fx is equal to a e to the power x, a is 0 and b is 1. So solution is fx is equal to e to the power minus x. Let's take one more example of this type. Find fx if its Fourier cosine transform is 1 upon 1 plus p square. So fx is equal to fc inverse of fc bar p. fc bar p is 1 upon 1 plus p square. By definition, this is equal to 2 upon pi 0 to infinity 1 upon 1 plus p square cos px dp. So differentiating with respect to x, df upon dx is 2 upon pi 0 to infinity 1 upon 1 plus p square del over del x of cos px, which is minus p sine px. Now multiply and divide by p, so df upon dx is minus 2 upon pi 0 to infinity p square sine px upon p into p square plus 1. Now add 1 and subtract 1, so we get p square plus 1 minus 1. Now break into two parts. Minus 2 upon pi 0 to infinity sine px upon p dp minus 0 to infinity sine px upon p into p square plus 1 dp. Value of this integral is pi by 2. So therefore we have df upon dx is equal to minus 1 plus 2 upon pi 0 to infinity sine px upon p into p square plus 1 dp. Now differentiating once again with respect to x, so d2f upon dx square is equal to 2 upon pi 0 to infinity p cos px upon p into p square plus 1, which is equal to 2 upon pi 0 to infinity cos px upon p square plus 1 dp, which is nothing but f of x from equation number 1. So therefore differential equation we get is d2f upon dx square minus f is equal to 0. So like in the previous problem, auxiliary equation is m square minus 1 is equal to 0. So therefore m is equal to plus minus 1. So therefore solution fx is given by a e to the power x plus b e to the power minus x. We want to find out values of a and b. For that we find out f dash x, which is a e to the power x minus b e to the power minus x. Now f at 0, if you put x is equal to 0, so we get f at 0 is equal to 2 upon pi 0 to infinity dp upon 1 plus p square from equation number 1, because cos 0 is 1. So f0 is 1, therefore a plus b is equal to 1. Put x is equal to 0 here and f0 is equal to 1. Similarly f dash 0 is minus 1 using equation number 2, because this term will become 0 and what is left is minus 1. So therefore from this equation we get a minus b is equal to minus 1. So a plus b is 1, a minus b is minus 1. Solving these two equations we get a is equal to 0 and b is equal to 1. Therefore fx is equal to e raised to the power minus x. Thank you so much.